this is how I actually designed my presentation. So these numbers are the reference numbers from the flowchart I have given you, and this is the reference to the IEEE paper writings. So if you just follow through that, you'll understand what I'm doing in the presentation, and that's some random content. So right off the bat, we should ask ourselves a few questions. So are cyclists really safe? So if we look at all the counts of the total number of cyclist injuries that has happened across the years in the United States, so it's consistently steady. It's almost near the 50,000 mark. So if you count that for 50,000 crashes a year, it's approximately 1.6 crashes a day. So based on what I thought, almost no cyclists ride in the nighttime. So if you think of like 12 hours as active hours of cyclists, it's almost like a crash per a day. So I thought that that's really not good. And so in 2017, 18.2% of the fatalities are cyclist or pedestrian related. So cyclists are definitely not safe. So why are the cyclists not safe? What makes them unsafe and why? So these are the results of a survey that has been conducted in 2016. Yeah, so when I asked for what made them feel threatened while cycling, so most of them reported that it was motorists. And when they asked for what did motorists do to make them feel threatened, almost all of them said that they drove very close to me and they were too fast. So the root cause behind this is all of the cyclists are riding on normal roads, and that's because they are having conflicts with motorists. So what should be done to solve this?
Can you explain, clarify, when you talk about accident,
Yeah.
is that accident with car or any vehicle with the bicyclist, or because of the bicyclist, other accident happens and bicyclist is not affected? That is more serious.
Okay.
They want to avoid.
Yeah.
Right? And in doing that, they probably in sudden movement, the car, they may not observe who is behind.
Yeah.
So that is bicyclist related accident. Are you talking about the accident only with the bicyclist?
So not related accidents. The accidents where bicyclists were injured or
okay. So only with the bicyclist.
Yeah. So what should be done to solve this? So again, those are the results of a survey. When they are asked, when more cyclists are asked for what are the changes that they desire in the community, most of them reported that more bike lanes would help the cause. And these are the results of an analysis that has been done. So as the total number of lane miles increase, the total number of cyclists increase, and then also the total amount of risk decreases. So it's evident that bike lanes definitely solve many issues, and so more bike lanes can reduce issues and can increase the safety without the need of police, and can also encourage in the end more people to become cyclists, and also improve the infrastructure. So the biggest question: how can we estimate this bike lane need? What are the things that has to be solved to estimate the bike lane need? So we can break this down.
Others, good question. So the accidents that you reported are on roads where there are bike lanes, or because of lack of bike lanes and the cyclists not paying attention to that, creating an accident? Is that more of your focus?
So actually, most of my focus is for accidents without bike lanes. But we also consider on bike lane accidents, and I'll explain shortly what's that's going to be. And there are actually many attributes in the data set that determines what was the reason for the accident. And so that involves bicyclists not visible, things like that. So I'll just shortly explain all of this. So we can estimate the bike lane need by measuring the frequency of how many bicyclists are using a specific road. And then we can estimate how safe that road is for the cyclists, to estimate the demand for a bike lane. So to estimate the cyclist traffic, so this question is actually a bit difficult. So to estimate cyclist traffic, there are multiple processes, but we actually kind of went through this procedure. So when people are asked for why they ride a bicycle in New York City, most of them reported that it was either recreation or exercise. But when you think of a person riding a bicycle for recreation or exercise, he just might go anywhere he wants. So his starting point might be his house, and he might go to a business specific area or a park. So we just cannot estimate his intuition. So we thought that estimating that part is really difficult, but when he goes for errands or shopping or commuting to work and school, it's easy to estimate because most of these areas are business related areas, so shopping and work. So we thought that the areas where there are more number of businesses, that areas will have more cyclists. So that's how we utilized the Yelp dataset. We found out all the businesses at a specific place, and then we estimated the demand for cyclists using that dataset. So what's the way that we can estimate the safety? So one way is that we can group all of the accidents into the roads, and we can estimate how severe those accidents are. And I'll shortly explain how we grouped all of those accidents. So what the proposed model does is, it splits the roads of a city into equally sized road sections. And then, as I've talked, it groups all of the accidents and businesses into these road sections. And then it uses experts' intuition to determine the severity of an accident's attribute. And it uses the weight of evidence formula. I'll shortly explain what weight of evidence means, to determine the importance of each attribute of every feature. And then finally, it estimates the score on a scale of 0 to 10 so that it's easily understandable. Where 10 is the worst possible case, or it'll definitely need a bike lane. So there's a lot of related work.
Can you go back?
Sure.
I just want to read.
Sure.
Split the roads of the city into equally sized road sections.
Yeah.
Meaning what?
So when you consider a road, for example, Rock Hill Road, so we divided Rock Hill Road into, for example, say 5 equally sized sections. And we did that based on the address numbers that we have. So for example, we have 5100 Rock Hill Road. And for example, say that there's an accident in 5100 Rock Hill Road, and then there's an accident in 5500 Rock Hill Road. We took all of that part into a single section. And I'll shortly explain how we did that. Yeah, so there's a lot of related work. So the context-sensitive design of bike lanes is an infrastructure approach. It considers several contexts of development, and so when considered for safety, all of the contexts. So that's one approach. And blue thermoplastic used to cyclist signs increased the yielding of motorists, and that kind of like increased the safety and improve the safety. And green colored bike lanes improved the total number of cyclists, and then it actually made the motorists look for any cyclists in that area because it's more visible. And the motorist to cyclist minimum distance of 3 foot on normal roads is a law in California. If you don't follow that, you'll be subject to a fine. So this also kind of like improved the safety. This is the score model. So this is a simple weight aggregating algorithm. It's frequently used by creditors to establish the credit worthiness of applicants. So these are several features, and these are the attributes. So what happens here is all of these attributes have specific scorecard points, and these scorecard points are evaluated using the weight of evidence. And these points help us in determining how good the person is for taking credit. So we've used some similar approach to estimate our final scores. I'll just explain how we did that. So another related work is the estimation of cyclist frequencies. So we've used this rough estimations from local households and commercial units. And another very efficient approach is using detectors such as cameras and video and processing and things like that. But for the purpose of our model, we just use rough estimations because though that's efficient, we just didn't have enough funding and resources to do that. So here's the system architecture. The architecture mainly comprises of 5 components and 2 data sets. So the accident data is the crash data set from North Carolina. The business data is the Yelp data set. And the 5 components are the geocoder, the evidence calculator, the address sectionizer, the accident severity module, and the score generator. I'll just explain with the help of the flowchart how all of the components work. So yeah, this is the flowchart. You can take the copies if you'd like to. And so yeah, so this is the crash dataset. So the crash dataset actually had multiple features in it, and we selected 9 most important features that are relevant in determining the severity of an accident. So some of the features are ambulancer, which determines if there is an ambulance assistance after a crash, the position of the bike during the crash, for example, like on a bike lane or on a normal lane, and several descriptions at an intersection or at a non-intersection. I can just show you a snapshot of the data set if you read.
In that, you have severity of accident.
And yeah. So it also has a feature called address. We actually kind of like needed that address column to determine the location, but I'll shortly explain why we did not consider that. So yeah. And then we have the Yelp data set as well to determine all of the businesses, but again we considered all of the only needed attributes. So that is the latitude, longitude, and then the stars and the total review count. So this will determine how good the businesses are at a specific location. And we just consider only these from the Yelp data set.
So you basically, selected subset of businesses in the
Yeah.
North Carolina area?
Yeah, in the North Carolina.
So you had kind of the boundary for where the accident happened?
Yeah. We considered only the city of Charlotte, the heart of the city of Charlotte. So yeah. So I'll just explain what the geocoder is. So we actually needed. So we thought of an approach that will use the addresses to determine the location of an accident. So we needed all of the address information for both the crash dataset and the Yelp dataset. So what we did is, so the addresses are not reliable. Most of the addresses had unknown information that are not correct addresses, and also both datasets did not have unique addresses for the same pinpoint location. For example, if this is Rock Hill Road, one of the dataset has Rockwood Street. Both of the addresses are the same, and we know that, but we actually wanted to find a process to merge them. So for that purpose, we just took the lat long of both of the datasets, and then we sent it to a geocoder to get the addresses. So that gave us like unique addresses for each location, and those are we just use those for determining the point of the crash that happened. So for example, these are the information from the crash dataset. So those are the lat long. So this is the dataset address, and this is the geocoder return address. So you can see it's almost the same. But if you see this address, this is not a correct address, and we got the correct address from the geocoder. So we use the geocoder to just clean the data. So that's the first part.
So quick question.
Mm-hmm.
So in your input data set,
Yeah.
that is about crash information, there you have regular address, right? You don't have lat long.
We do have lat
Oh, you
long.
had
and
lat
then-
long there also?
Yeah, we have lat long and address.
I see. The lat
Yeah.
long and then the actual address. And then in your Yelp data set, you...
Have both once again.
Okay.
But we actually need to clean them. So for that purpose, we just sent the lat long to the
Now,
geocoder.
tell me this, your crash information is coming from several years ago, and your Yelp data set, is it current?
So I think it's so that's actually also an aggregation of businesses from several years, but
Yeah.
I think that's 2016 information.
So from Yelp?
Yeah.
And then, because I saw crash information such as 2012 in
Oh,
your
okay.
data set, so I wonder if they are temporally consistent.
Okay.
Because the business has changed, right? Restaurants
Yeah.
keep changing,
Mhm.
but that's something to keep in mind.
Yeah. Sure. So yeah. So the next part is the address sectionizer. So this is the part that divides all of the roads into equal sized road sections. So I'll just explain how we did that. So we have the address numbers. We kind of like fixed the address name, and then we divided the address numbers in such a way that each 5 streets are considered to be a single road section. So for example, we just created road sections for which bike lane needs can be estimated at the end. And then we included all of the crashes and then the businesses into those address sections to estimate the demand. So these are sample addresses. So what we did is, so this is 5000 Home Street. So imagine that this address point has like, so imagine that there is another crash at 5100 Home Street. So what we considered is we took the floor of 5000 and then we took the seal of 5100 in such a way that their thousands are matched. So 5000 Home Street is going to be the start point of the road sections, and then 6000, because the thousands are being sealed, is going to be the end point of the Home Street. So and then after we have considered the bounds, we just split them into 500s so that 5 streets are considered. So we just use those numbers to easily split all of the roads into sections.
So you just go by looking at the number and then split that across. So you take 2 accidents,
Mm-hmm.
and then the segment between them, you kind of split it up.
Yeah. So essentially, what those 2 accidents are going to be are the minimum number and the maximum number that has happened in a single road section address number, so that all of the other address numbers can be in the middle, and we can be estimating all of the accidents with all of the bike lane with those accidents. So I'll just show you what we did. So
Actually, one road have you considered? You see, some roads are 2 lanes, some
Mhm.
roads are 1 lane.
yeah.
Have you considered the type of road or number of lanes?
So we actually kind of like, so there's actually an attribute that determines if the crash happened because of an oncoming vehicle or because of an ongoing vehicle or things like that. But we kind of like did not consider how many lanes the road needs.
Because homes had 2 lanes. Some
Yeah.
places, some
Mhm.
places only 1 lane.
Yeah, that's right. So
So how your data experiment or algorithm
Mhm.
affect?
so we should be kind of considering that, definitely.
Yeah, you need to do some assumptions that
Mhm.
this is our assumption.
Yeah,
You cannot include all the realistic scenarios.
Yeah.
So one thing I see a problem is,
Mhm.
when somebody starts biking, I mean, there is a source and a destination, right?
Yeah.
They need bike lanes throughout. It's not like you can put bike lanes in certain sections of the road and not have it in certain other sections.
Yeah.
So in addition to the accident information, right? I mean, if you knew where people usually start and end, that's
Yeah.
when you can properly say where bike lanes are needed.
Yeah.
Because you really need it for all through.
Yeah,
But
that's
maybe
right.
not cost effective because
Yeah.
the
Mhm.
city may not be willing to
Yeah,
put a bike lane all through. But any place where there is no bike lane is a risk.
Sure.
Yeah, there is a definitely.
Yeah.
So,
I want to jump in here. So that definitely, this is a great point, but in many bigger cities, I mean, what people do is they park their bike somewhere and then they take public transportation. So it's the trip is not necessarily entirely.
Right. I mean, still,
So that's-
to the bus
that's
is
your
their
point.
end point.
Sure.
Like I would
That's a
prefer
great
to
point.
have a bike lane throughout.
yeah,
the
but
road.
that's really
But it may not be cost effective.
Yeah.
Sure.
But the density of routes
Mhm.
can help you
Yeah,
say
yeah.
that at least this part, if you put the bike lane, it's going to reduce the accident rate
Yeah,
by
yeah.
some number.
Yeah. So that was the approach that we
There is
considered.
a related point here. You see, your observation is
Mhm.
you should have a bike lane or you should not have a bike lane,
Yeah.
right? Yes or no?
Yeah.
Sometimes it happens that there is a bike lane, but that bike lane needs to be extended because the road traffic has increased from that section where there is no bike lane.
Yeah. Mhm.
Is there any thought about extending an existing bike lane to?
So we actually did consider the roads with bike lane and without bike lane.
Yeah,
So-
but not expensive.
No, so
Okay.
that'll kind of like involve that, because if a road that does not have a bike lane and that part of it before has a bike lane and that specific part gets a recommendation, it's just that it just needs to be extended. So it does involve that. Yeah. So any more?
Keep going.
Yeah. So yeah, this is how the address sectionizer works. So what we just did is we just took the minimum and maximum of all of the accident occurrences based on the geocode information that we got. And then, as I've informed you, I've just applied the floor and seal. And then I've just divided that into groups of 5 sections. So Camp Stewart Road will be having groups of, so 30th Camp Stewart to 30th Camp Stewart is the road section. So some of these are, so all of these are imaginary road sections, and some of these might not exist because we don't know if 30th of Camp Stewart is existing. So that's a small problem that we should be taking care of. But as these are imaginary, it's okay. So the accident severity module. So this is the module where the expert comes in and then he looks at all of the data set and he just determines how severe those accidents are based on a scale of 0 to 5. And so 5 meaning the accident is real, and the attribute is really severe for the accident. So so this is actually a feature that we have, bike direction. So facing traffic gets a 5, with traffic gets a 3. So these are just random scores that we have given. And these scores will be the basis of our estimates in the end. These will get aggregated by a module that comes after the score generator. So these are the main things that an expert should be assigning so that we just sum them up at the end.
So if there is a accident that
So I'll just show you.
Yeah, there is an attribute related to the injury and how severe.
Yeah, I will just. So if there is an ambulance where yes or no, I guess gets a 5, no gets a 0, and then crash group. So several other attributes that are just given.
I
weight.
see.
Yeah. So these will be aggregated in the end for the road sections.
Does your data set have any information about the weather at that time when the crash happened?
Actually, no, but we should be considering that in the future. So that it will be more effective. So the estimates will be more effective.
Because I've seen a cyclist on one of the winter days when I was driving on Emmanuel Cleaver Boulevard. It's icy, there is snow, but the guy still decides to drive his bike and he slips and falls. And there is traffic flowing, you know. I don't know how somebody can ignore the weather warning and take their bike. Maybe that was the only thing that they could afford to do.
They may have some constraint their situation and all that.
Yeah.
So what did you do?
I just saw him and thank God he didn't come under a car or my car.
I had a similar situation, but not with the weather, with the scooters. I mean, there are no bike lanes in many roads in Kansas City, and these scooters, I mean, they get everywhere, very close to cars, and one gets really scared.
Right. I mean,
Yeah, I won't tell you my experience because I was involved, so continue.
Oh, so he can attest your results.
Yeah.
So were you on the bike or in the car?
I see road.
But you survived. We can see that.
That's why you can see me here.
Yeah, okay. Where's the, So the evidence calculator, so this is actually an important part in the thesis. So I'll just give you a simple example. So imagine a cyclist is riding on a normal lane. Imagine 2 situations. There's a bike lane on one side and there's no bike lane on the other. And if the cyclist wants to take a left, so he should eventually come into the normal lane because he just can't take a left on a bike lane. So if that happens, the crash. So if that happens and if there's a crash involved, So bike lanes cannot help in solving these types of crash. So there are all of these, there are some specific attributes that need to be weakened for this purpose because bike lanes are just not helpful in that case. So for that purpose, we designed the evidence calculator. We just evaluated the predicting power of all of the attributes that we have. And we did that using the weight of evidence formula. So what the weight of evidence formula does is it just takes a distinguishing situation. So in our case, it's going to be a bike lane. The road has a bike lane, and then our road does not have a bike lane. And then it just checks for the distribution of that specific attribute. So imagine if the non-events are a guy taking a left and there's no bike lane, and then a guy taking a left and there is a bike lane. So obviously, both of the values are going to be almost equal. So the value of weight of evidence is going to be equal to almost 0. But if there are a lot of accidents that happen in this situation, that means without a bike lane, and there are less number of accidents in this situation and with a bike lane, that means bike lanes are helping the case. And in that situation, we'll be having a positive weight of evidence because it's a natural logarithm. And so what we decided is if the weight of evidence value is positive, we just wanted to not weaken all of the values that we got from the accident severity module that are given by the expert. But if the weight of evidence is like almost close to 0, or if it's negative, if it's the worst situation, we just wanted to weaken those scores. So for that purpose, we just used the weight of evidence formula. And then so these are the examples of what we've done. So there is actually a small issue with the weight of evidence form. So those are the distributions as I explained. So this is a without bike lane, and then this is with bike lane. And these are all the weight of evidence values that we got. And the small issue that we had with using this weight of evidence formula directly is it just does not consider the total number of occurrences of the accidents. So imagine if there are equal distributions of 2 different attributes, and one of them has a total number of more accidents. They're going to have equal amount of weight of evidence. So and we thought that the accidents that the attribute that have more accidents should be given more weight. So for that purpose, we just added the total. We added the total number of occurrences, and then we just multiplied it to the weight of evidence.
So tell us a little more about the columns there. W lane
Sure.
is the
With lane occurrences. For
how many
attributes.
occurred, and then without lane.
Yeah,
I see.
these are with lane and these are without.
And then the score, positive score, indicates that lane is helpful,
Yeah,
and a negative score indicates that the lane did not
yeah.
make
Lane
much
did
of
not
a
help. Yeah.
difference. Okay. Although, like, if you look at motorist overtaking bicyclist.
So bicyclist left turn merge, the example that I have given. It's
Okay.
it's having a negative. So that's how we kind of use this values, but because this does not consider the total number of occurrences, we just wanted to multiply those occurrences to the weight of evidence value, so that with that value we can try to weaken scores given by the expert.
So you're saying that assuming each of those events is not equally likely to happen, you kind of weighted it based on how many times it really happened.
Yeah.
I see.
Yeah.
Mm-hmm.
And then what we eventually did is we just converted these values to a thing called importance factor.
Mm-hmm.
So what this importance factor is, like, if we have a positive value of the weight of evidence, it's just going to be 1. And then if the value is negative, it'll just reduce based on its magnitude. And then we'll just multiply this importance factor with the scores defined by the expert, so that if a value is more than 1, if a value is 1, then it's not going to get weakened, but if it's less than 1, it's going to get weakened because it's simple multiplication.
Can you go back to previous slide?
Sure.
The largest value I see, motorist overtaking bicyclist,
Mm-hmm.
width lane is 105.
Yeah.
Now, when width lane, that means there is a bicycle lane, right?
Mm-hmm.
What is the meaning of overtaking there? Because the bicyclist is riding on his lane,
Yeah.
or her lane. The car is on its own lane. What does it mean by overtaking there?
I probably think that so there might be 2 lanes, and the motorist might be behind the bicyclist, and he might not see while he was driving, while he was like taking the right or.
But bicyclist driving on its own lane.
No.
Which lane
Yeah.
you're talking about? right?
Okay, so the 105 occurrences.
Yes. So with lane,
Yeah.
I'm bicyclist. Okay.
Mm-hmm.
I would always like to ride on the bicycle lane,
Yeah.
and there is a motorist here.
Mm-hmm. Yeah.
So motorist will never cross the line.
You never know. People,
Yeah.
the
That
way
might
people
happen.
drive, they even
Yeah.
though they tend to be in their lane, but they may be very close to the bicycle lane,
Yeah.
and that's where they might have tipped.
I think it may happen when you want to take a right sometimes.
Yeah. Sometimes. Yeah.
Right. So
That's why, like, I lived in Denmark for like 5 years, and
Mhm.
there are bike lanes there everywhere.
Mm.
So when you drive, they tell you have to check your right blind spot.
Right.
So, especially when you take
Okay.
a yeah.
So, but that is one occurrence. But
One occurrence.
still,
But
even
that's
with
not
the
the only-
lane, you
that's
can
not
go
the only
hit the
situation.
bicyclist.
Yeah.
It is possible when you are
Yeah.
driving along the same side. Because you
okay.
may get very close. Sometimes the bicyclist may be not fully in the bike lane.
Yeah.
Those situations, there are infinite number of things might happen.
Sure.
Okay.
Yeah.
Bicyclist singing song, something, everything distracts.
Yeah.
Everything is a distraction. But what I want to understand,
Mhm.
what situations have you considered?
So all of the situations that that are in the data set that would help in determining how severe these accidents are. So there are 9 of those features that I've shown you in the first slides. So should I?
No. So you have considered, similar set of matrix for all negative numbers.
I didn't get it.
No, as you said that you have considered several parameters. Right?
Mm-hmm.
So for every negative sign, for example, motorist overtaking bicyclist, bicycle right turn, merge and all those,
Yeah.
you use the same set of parameters to get the numbers or?
Yeah. So are you asking about the formula or about the data set?
No. Let's continue.
I want to clarify.
Okay,
So-
yeah, go ahead.
Basically, tell us a little more about, each row in your table and each column. Tell us again clearly,
About all of these?
not the right side,
Right.
sorry, the left side.
What situation did you consider, okay, so that you got this data? Motorist overtaking bicyclist. One situation that bicyclist might have crossed its own line.
Mm-hmm.
The motorist might have crossed its own lane and
Yeah.
hit the bicyclist.
Yeah.
These are the parameters.
Yeah.
Okay.
Mm-hmm.
What other parameters did you consider? And if you have considered, let's for example, 10 parameters
Okay.
for possibility of an accident.
Mm-hmm.
Did you consider all those parameters for all those things like motorist right turn, loss of control? So same set of parameters.
So,
Yeah. So we computed this algorithm for all of the features that we have in the data set. So yeah, same set of.
So basically, what he's doing is, in his data set, this attribute that you see in the table, that each
Right.
statement
Yes.
is put with every record, accident record.
Yeah.
So he's basically just aggregating all of it,
Yes.
right?
Yeah.
So he's not kind of breaking it down into finer situations.
Yeah.
Yeah.
So your
I'm
answer
just
is no.
Okay.
Your answer is no.
Okay.
It is taken from the data set as is, and you have
Yeah.
aggregated how many
Yeah.
times it was reported in the data set that the bicyclist right turn / merge,
Yeah.
or motorist left turn / merge.
Yeah, so you see.
I'm sorry.
Because many parameters may not apply for certain categories.
Right.
Yeah.
Okay.
Yeah. I'm sorry about that.
So we are paying attention. We are not sleeping.
So yeah, so this is the important factor. So we'll just multiply this with the values given by the expert. So the score generator is the final part of the model. So what it does is it simply aggregates all of the scores for all of the accidents and then the businesses, and then it just combines them to the address sections that we defined earlier. So yeah, aggregate all of the previously calculated metrics. So as I previously informed, we just calculate the attribute weights, and then we just replace them to all of the features that are there in the crash data set, and then we just aggregate all of those values to the address sections. And so the final score is just going to be the summation of all of these columns that we have. So while considering the Yelp score, we just filtered out all of the businesses that are rated for more than 100 times, and then we just added all of the ratings of those businesses. So this address section might have a business that is rated 4, and then it might have been rated by more than 100 people. So that's why this Yelp score has a 4. So that's how we came up with the Yelp score, and these are the final section scores that we have obtained. So you might actually ask me, so which is more severe in this? Is 55 severe? Is like 59 severe? I'm just not understanding what those values did. So for that purpose, we thought of like normalizing all of those values to a simple scale so that it can be understandable. So what we did is we looked at the distribution of the scores, and we kind of like figured that there are a few outliers. Here's a 230 score for a single road section. So we kind of like rejected all of these outliers, and we thought that the scores are somehow kind of like stopping at this point of 100. So we thought that any road section that has a score that's beyond 100 is bad on itself. So we just replaced all of these values with 100, and then we just normalized this scale. So and then we just simply use the min-max normalization technique to do that. So minimum is going to be 0, and then maximum is going to be 100, and then anything that's above 100 is going to be 100.
So I can see the gradual decline, let's say from 20.
Mm-hmm.
There is a bump in 80, and suddenly there is 90. Why that significant difference?
Probably there might be more accidents in that specific section. More types of like, so the first part might be there are few less severe accidents, and then this part might be in the middle point, and then it gradually decreases. The score values gradually decrease. It's just that the severity of the accidents might have been varied, and I just don't know why there is a small bump in 90, because it just depends on the data set. It just depends on the crashes that happen. So we just thought that 100 is the bounding point.
You know, when you answer a question like this,
Mm-hmm.
don't say I don't know. Okay?
It's
You have done the research.
yeah.
So it's very good to say that I observe these possible reasons.
Okay.
They may not be accurate, they may not be.
Yeah.
But at least you have thought about it, you have looked into it,
Mm-hmm.
and you have reason to believe that
Yeah.
these are
Yeah.
probably possible
Okay.
causes.
Okay.
Don't say I don't know.
That was just spontaneous. I just didn't mean to.
You are honest, that's good. I like honesty,
Yeah.
But tell us a little more. It's kind of not very clear to me after you got the weights, what did you do? So can you go back
Sure.
2 slides?
Yeah,
So,
sometimes you see honesty penalizes you.
yeah, especially if you're a politician, if you're honest, you get penalized very badly, and you know which country I'm talking about. But tell us,
Yeah.
Okay, you have these streets, and then you have the sections of the street,
Yeah.
and then that's all the remaining stuff is the attributes coming from your data set,
Yeah.
plus the Yelp
Yeah.
score,
Mhm.
and then for each attribute coming from your crash data set, did you replace that value with
The attribute severity score engine bonus stuff.
Okay, so you basically gave each attribute a weight, and then you just multiplied the attribute value
Yeah.
with the weight, and then
Yeah.
you summed it over
Yeah.
all the columns
Mhm.
to get the section.
Yeah, and I actually forgot a point. So
Some of the weights got weakened as well.
yeah. Some of the weights got weakened because of the attribute weight multiplication. And so what we actually did is because we have the point values, exact point values of the accidents, we just took those address numbers and then we matched with the address section so that they fall into a section and then those values get aggregated.
So
as the
these
numbers.
real numbers you have, these are after you multiplied them by the weight.
Multiplied and then aggregated.
Aggregate, yeah.
Yeah.
So if I add all of those numbers, I should get what you see.
Yeah.
Okay. Yeah, because I wasn't expecting 2.59 in your original data set.
Yeah, these are just
These are
multiplied
after
and
you
aggregated.
updated.
Yeah.
Okay. All right.
Yeah.
And then what happens?
And then we just normalize these scores.
Okay.
Yeah, and then we just took 100 as our bound and we normalized our score.
I mean, you didn't have to throw the outliers because you could have just normalized it by considering 240 as your.
But we thought that that will distort our scale of 1 to 10. So that's gonna like have less severe accidents in like 1 to 2.5 and then very severe accidents in.
So in
10.
general, these events supposed to follow some kind of skewed distribution, right?
Mhm.
So that's what your chart actually shows.
Yeah.
So there will be few that have very severe but very rare. You know, how many severe accidents do you have?
Yeah.
So I wouldn't throw them as outliers. I mean, I
Okay.
don't know. I'm not very convinced why
Oh, okay.
you want to throw them away.
Okay,
rather
so why we did this approach was like we just thought that getting a 100 score is really bad.
than,
So we just thought that we should not kind of like look like a low on them. So we thought that those are severe on them themselves, and then these are very severe as you just said. So we thought that 10 is the most severe score that our model would be assigning. So we thought in that way. So we just
Others, can you perhaps describe like a score of 100, what it actually means?
yeah. So the score of 100 determines like, for example, if there are 2 very severe accidents, for example. So imagine all of our accidents get a 5 score from the severity expert, and then they just don't get weakened. And then there are two occurrences like that. So that's because we have 9 features. That's gonna give us like so that's gonna give us a 90 score because each value has 5 as its max value, and then we have 2 accidents, and then consider 2 more businesses in that space, and that's gonna give us like 100 score. So very very severe accidents and then very important businesses in a road section is gonna give us 100. But these are just imaginary values; those never happen in the real life. And if a road section has 100, then that might have had multiple occurrences in that space. So we just thought that 100 is going to be our bound. We thought that.
For me, 100 is just a number, right? I mean, it's
Yeah,
just
that's
you're
right.
multiplying some weights
Yes.
and with some values, and if I add more features, that 100 will become 500.
Yeah, that's right.
And so it's doesn't make any difference
It's
to
a
me.
relative, it's a very relative.
Yeah,
Because
so-
ultimately you then try to normalize. What is more important is this distribution.
Okay.
This is what says, to me, like, kind of gives me an idea about section scores.
Yeah.
But section scores and them being skewed like this, what does it tell me? Does it tell me anything about
Yeah.
accidents?
Mhm.
Does it tell me anything about? So most of the accidents tend to be not very severe.
Mhm. Yeah.
Is that what I can interpret
Yeah,
from this
yeah.
chart? Okay. And then few of them are extremely
Yeah, few of them are really
severe.
severe. Yeah.
Okay.
Okay. Yeah. So yeah, based on what we actually thought, we just normalized them, and then we got like a score in the range of 1 to 10. So these are just the visualizations of the non-normalized score and then the normalized score. So this is the score estimate, and so we can see that this specific accident had like a very high score because and it's non-normalized. So these are the total number of accidents in the area, and then this complete bar shows the total number of accidents in businesses in that area. So we can kind of like see the different types, different numbers, and then the score going down. And that's actually dependent on the several data attributes that we have. So yeah. So these are our final estimates.
Of
Final score estimates of if the road needs a bike lane or not.
I see. So these are the actual score.
In comparison to the number of accidents and the number of businesses. Right?
Yeah.
So basically, this tells some, let's say, a city planner that okay, these are the different segments, and these have higher scores, so you need to put a bike lane, or these have lower scores, you don't need to put a bike lane.
Yeah.
And so basically, your model that you mentioned is the whole process of taking your input data, giving a weight, scaling the weight, then coming up with a equation that sums all the weights and across the attributes and gives a score. Why didn't you use a traditional machine learning approach? Let's say logistic regression.
Yeah.
Why didn't you just apply that with the data set to make a prediction whether certain roads, certain sections need a lane or not?
Yeah.
I'm thinking, if I were to do this,
Mhm.
I would probably approach it differently and then compare it against what you have done. So do you have how do I know that your score estimates are genuine?
You've tried it.
Yeah, so I actually tried it, so that's going to be the next model.
Okay. Okay. I thought you stopped here and I didn't realize. So we haven't yet gone past half of his thesis.
No, it's almost done. So,
Okay.
so this is the final part. So we actually took the estimates that we have taken, that we have calculated until now, and then we just implemented a few models. So we converted it into the scale into a classification scale, and then we just.
Don't use the word just to kind of trivialize effort. Don't use the word just.
Yeah. So we converted the scores into 4 classes, and we implemented 4 models.
Use 4 models, and then which one has the highest score?
So support vector classifier, and then of course
they did much better.
Yeah.
And don't need a bike lane, might not need a bike lane, might need a bike lane, definitely need a bike
that's
lane.
just a simple.
So did you do cross validation?
No. We just,
How was your training and test set, split?
So we totally had 1,000 road sections. We took around 600 into training and then 400 into testing.
Testing, okay.
Yeah.
So you may want to do cross validation. You know what is cross validation?
Yeah.
You take a random piece and use it as test.
Uh,
you
so-
train on the remaining.
So I think that the model that I've done this using Python. So I think the functions that I've used do cross.
Yeah, it is there. It is there.
Yeah. So it is there. So.
That way you get a kind of a more general score that you can believe applies across the whole data set.
Yeah.
Okay.
Yeah.
So Dr. Kumar had a
Yeah, no,
question.
just a simple thing. You are saying, so let's take 7.5. In
Okay.
one row, it says might need a bike lane, and same 7.5 says
Oh.
definitely need a bike lane. Which one I should
So consider like a normal C type bracket over here and then a square bracket over here. So this is going to be 7.5 is going to be in this state, and then 7.4999 is going to be this. Yeah. So yeah, this is the end of the thesis. In the future, we just didn't focus much on the data independent model, the statistical models. We actually thought of like implementing some kind of different machine learning algorithms. We should do that in the future. And so we actually have just 9 features right now. It would be really great if we have more number of features by getting another essential data set.
My curiosity is, why did you need the scores in the first place? I can take that input data, and I'm just trying to be devil's advocate here, just giving you a hard time because this is the last time I'll probably give you a hard time. So after that, but I want you to think also. In my general situation, right? I have this data set.
Mhm.
I know where accidents happened and where accidents did not happen.
Yeah.
I mean, those are all the other
Mhm.
locations which are not in the data set. Right?
Yeah.
So I can, use my input data set to build a model
Mhm.
using whatever features are available to predict whether bike lane is needed or not.
Yeah.
Right? And then I have to show that to some domain expert.
Yeah.
Okay?
I got you.
Or I could look at what has happened over time. Did eventually a bike lane get put in that area over time? Because you can probably get that information from your maps or some other way. But I want to, because now what you're doing is you're proposing a score and
Yeah.
reusing that to evaluate your model.
Yeah.
So I feel, what if your score is not
in the
the
first
right
place.
thing,
Okay.
So I'm kind of, deliberating whether can I believe what your output is correct. I'd rather go back to raw data, make a prediction on whether
Mhm.
bike lane is needed or
Yeah.
not, and then take parts of the data that I already have, and then I use that to verify,
Yeah.
against my prediction.
Okay.
That way, I can be sure that you predicted purely based on the data set and
Yeah.
not on something that you created, which sometimes is a little challenging to
Mhm.
believe. Okay?
So the main purpose that we came up with this course instead of implementing the machine learning model at the first itself is ease of readability. So most experts in the Department of Transportation might not know what a neural network is. So if we kind of like show them a simple score estimate, that's just simple aggregation of several things. We thought that will be easier for that person to understand. So that's why we went with this course instead of using a machine learning model or something like that. And that's actually why creditors still use the score aggregations and things like that instead of using machine learning approaches. So
No, but the way they compute scores is very sophisticated, right? They consider
Yeah.
different parameters. They see who defaulted and who didn't default, and what attributes played a role in them being a defaulter or not.
Mhm.
All those are considered to come up with a score. Score is just a number.
Yeah.
In fact, if you had run your model on the data and produced a score, I would buy it, because that's giving the planner some number that says you must or you may not.
yeah.
But if you put the score before you even train,
Mhm.
I kind of get a little confused. Okay, I'm not. That's because I'm not seeing a traditional approach being
Yeah, yeah.
followed. But you may have some reasons for it. I just don't know what they are.
Okay.
Okay, and you need to think about it. If you
Yeah.
have to publish such a work, it better be
Yeah.
very thorough.
Mhm.
Otherwise,
Okay.
they will reject the paper.
Okay,
And I'm trying to help you by giving you tough comments.
Yeah.
Yeah, you need to do that. See, I've seen papers published in SICKDD, it's a top conference in data mining, where they had a data science track for solid applications in real world. So one of them was from multiple universities along with the firefighting department. So what they did was they came up with a model to predict which buildings may catch fire,
Okay.
over time, because of certain building parameters, either violated, not
Okay,
followed,
okay.
etc. So they had a real data set of all the fires that happened. They
Yeah.
went back in time and then they trained on this data
Yeah.
and they made predictions. And then they tested it or verified it against whether a fire actually happened or not,
Okay.
to say how good their model is.
Okay.
Now you can take that model and give it to a firefighter and say, you run this model on all the other
Yeah,
input
okay.
locations that you have, and then hopefully the prediction is
Yeah,
still
yeah,
correct.
yeah.
Okay, so that's believable, right?
Okay.
So I want to see something like that. I
Okay.
want to see, if you, again, it may be very challenging. You may not have history of when a bike lane was added, but
Yeah.
but at least if you could split that data set and keep track of all the accidents that happened maybe before 2015 or 2016, and then train on that and make a prediction and check whether there were any reported accidents in 2016 and beyond, then I'll believe that your model predicted correct.
I want to jump in. I think.
I mean, I'm just
sure.
kind of.
No. This is a great idea. I mean, it's definitely something that we consider, but fortunately, we lack of data.
Right.
That's what I want to say.
Yeah.
No, that I completely understand.
Yes.
That you probably don't have the data, but if
It
you want to
took
go
us a
ahead and
long
publish
time
it,
to find this data
yeah.
set.
If you want to go ahead and publish this, and I expect that you'll publish it in a good place,
Mhm.
you kind of redefine your
Okay.
problem. And,
Yeah, sure.
You know, so you should finally be able to verify your output with reported data that this happened
Yeah.
or did not happen.
Mhm.
Then people will say your model is.
Okay. Okay.
That's a
Yeah,
great
sure.
point.
We'll,
Yeah, that's a great point.
yeah, we'll try to do that.
So you have some visualizations as well on the demo?
Yeah, I'll just show.
Yeah, really quick because
Yeah. So this is just a small visualization. We've taken 0 to 2.5 into green color and 2.5 to 5 yellow, 5 to 7.5 orange, and 7.5 to 10 as red. And then we just plotted this across a single street. And then we got this result. These are just the estimates. These are just the final estimates, final normalized estimates, and then we visualize them.
the other one is like dots, I think, it shows.
Yeah, so we actually had a API limitation that would limit us to doing this for 10 road sections, so we are not able to do this for the entire city of Charlotte. So we are, however, able to do dot representation of the start points of that intersection. So these are some specific areas that might definitely need a bike lane. So there are some red spots all over the place.
So based on your scores, right?
Yeah, based on
high score. Okay.
Yeah. And so if you want me to go through some of the code, I can just go through.
It's up to the panel.
No. Code is. I know it runs. Okay, that's why I produced.
So can I conclude here then, because the center of the map is more crowded area, right?
Yeah.
More congested.
Yeah.
Outside, on the east side, you have less congested area,
Mm-hmm.
traffic-wise.
Yeah.
So, is it that you need bicycle lane, same amount compared to this congested area? Because that's what I see, I may be wrong.
So that's actually, so there might be multiple number of accidents in that specific spot that's leading to that red spot.
And maybe some of the areas in downtown have, they already have bike lanes.
Yeah, they might already have the bike lane.
So on top of this, following up what Dr. Kumar asked, do you know how many accidents were there in each location?
We can actually look into. Yeah, so for one, we had 3 businesses and 3 accidents, and those 3 accidents might be in this area, so that it leads to that. So it's somewhere, it might be around like 7.5 or a little more, and that's why it's all around 20.
The problem is we're very limited with the data set that we have.
Yeah.
Unfortunately, I mean, you were looking like for a month to find a good data set.
Yeah. Took a lot of time to get it.
Yeah, what Praveen sir suggested, that might be a better approach to compare your result with whatever data set we have.
Yes.
You know,
Yeah.
So you sent the paper already, or you're working on it?
We sent it. We're not necessarily expecting, approval from the first round, so
Mhm.
we might get some suggestions like yours. And we'll look on the work and
Mhm.
see how it goes.
Yeah, we'll just implement whatever you said, and then we'll try to change it so that it's better.
Look, I would suggest, more than what I said, look at papers that have been published in good places. See how they came up with an approach
Yeah,
to
okay.
train and test, and then you can mimic that, okay?
Yeah.
Certain features may not be very useful. Sometimes when you have large number of features, you're training certain models, you may not be doing a good job, so then how do you select the most dominant features? That's
Yeah,
that,
yeah.
and then you do the training.
Mm-hmm.
Unless you're doing deep learning where anything can go into the deep learning model.
Yeah.
Okay? So read those papers first,
Yeah.
and then see how they approach the problem,
Sure.
and try to give your uniqueness of bike lane prediction by following something similar or maybe something with relation. In fact, you should look at this project from NYU. There's a professor, her name is Juliana Ferry. She's become very successful in visualization, databases, and other aspects. And her project is, one main project is with the Department of Transportation in New York City.
Okay.
And they have tons of data about taxi trips.
Okay.
And they help, and their software called, I think it's called Viz Trails, it helps the city people figure out where to put the resources. Okay? So, she was giving a keynote recently at ICD, and she talked about the predictions they make, and the transportation department loves it. They are actually using it in the real world. I mean, it's being used.
Okay.
And they sometimes, for example, one of the challenges was in New York City, when the weather is bad, getting a taxi is very hard.
Yeah.
Okay? So how do you place your resources correctly so that people can get a ride when the weather is bad? Okay? So, and also, the efficiency of the whole system, the transportation system can be assessed. So something like that is where you are headed.
Yeah.
So
Yeah.
draw some inspiration from that
Okay,
work,
sure.
in my opinion.
Perfect.
Really
That's
good.
valuable advice, yeah, absolutely.
Yeah. So,
Any questions from the audience?